Okay, well, I see by the chatter in the classroom that today is the merge sort algorithm is due, and so it sounds like there's some questions about how to get it to work. Okay, so now remember, we've mentioned this several times before, but remember, the temporary array is already provided for you, so don't try to do your own temporary array. And also, the split is already done for you, so don't try to do the split. It's all you got to do is implement the join. So let's take a look at figure 4.11 and see how to implement join. Now here is, and I actually said the code last time. If you will listen very carefully, here's how to do it. First of all, there's only one loop, and the control variable is k, and it goes from what to what? From low to high. So you can write a for loop to have k going from low to high, right? Including low and including high. Oh, one more thing. We also have to initialize I, and we also have to initialize j. Because the split told us what m is. So here, we initialize I to the first element of the left segment, and we initialize j to the first element of the right segment. You see in part A here, right? So that's a couple of assignment statements there, right? And now, do we know right away, off the bat, that we should check, that we should test a sub I with a sub j? We do not test a sub I with a sub j right off the bat. Why not? Because as we're going through the loop, I might be greater than what? Okay, so here's the code. If I is too big, do what? If I is too, you know what we mean by too big? If it's past where it's supposed to be, to where you're doing a comparison. If I is too big, then what do? You copy what? You copy j down. Else, if what? J is too big. Let's not say the. Let's not actually say all the code. Otherwise, else if j is too big, do what? Copy I down. Else, what do? Else you can do what? Else what? Now you can compare. All right, now that should be enough to, I almost did your whole assignment right there. You just got to do it. You just got to do.
So how the program is already coded, it takes care of it takes the array of numbers and it splits it at the get-go. So all we do is the join.
That is the whole point of the template method pattern. Sort has been written. Yes, yes, yes. I'm glad you emphasized that again. This happens all the time. This happens all the time. You want to do, I'm not asking you to do the merge sort. Sort has already been done. It's the template. The sort is the template method. And we are doing, and the split and the join are the primitive methods. And the sort has already been written. Is everybody clear now? All right. So now, I think that should be, and you only have one loop. And of course, so here in figure 4.11, in part A, we compare I is not too big and j is not too big. So what we do is we compare a sub I with a sub j. And so now in this case, 20 is compared with 10. 10 is less than or equal to 20. So we copy the j over. Oh, and by the way, and we have to increment j, right? But the k will be done with the for loop. The k is the control variable. That will be done with the for loop. And so on in parts B and C and then D at the end. All right? And then E, part E of the figure shows that after you're all done with that, not nested, but after you're done with all that, you copy the values, okay, from the temporary array back up into the original one, between low and high. Again, everything here is between low and high. Also, it's not between 0 and whatever, it's between low, because recursively low and high change. So you're doing just little parts of the array. You're merging little parts of the array back up. All right, now, is everybody, any more questions now about merge? How to do merge. So, the next thing I'd like to do is show you, so what you should be doing is you should be using the sort int project to test this. And so I want to just demo sort int for you. Okay, so here's our demo. And the project that we're going to use is sort int. The project we're going to use to test these sort algorithms. And here over in under the Files tab, if you go under sort int, you can see that what we have is a bunch of files with numbers in them. And these are integers, so we're sorting integers. So here's this file I010 has 10 integers in it, and here this one has 100 integers in it. And I think what we're going to do is I'm going to demo this file I050 that has 50 integers in it. So you can see that they're all integers and they're not sorted. So if we go back here under projects to our sort int, we can actually see the main program. So here's the main program, the sort int main program. And let's take a look at what it does here. You see what we have is an array T of integers. So here's our safe array of integers. And then we have a pointer to a sorter, to an abstract sorter, right? And then we prompt for the file, etc. And then what we do is we ask the user what kind of sort you want: merge, quick, insert, select, or heap. And then check this out. In the main program, it says sorter gets new if you type M, sorter gets new, merge sorter. And then down here, we do sorter, arrow, sort, array 0, length minus 1. All right, because we get the length from the previous code. So so here is how we do. Now here's my question: when we say sorter, what is the type of sorter? Trick question. It has what? How many types? What is sorter?
Type T could be a merge sort, helper sort.
Yeah, it could be a merge sort. Yeah, so
5.
well.
But it has
Well, yeah. How is sorter defined up here? Look, how is sorter defined up here? Here, when we say sorter here, what is it? It's a pointer to a what?
An abstract sorter.
It's an abstract. So is abstract sorter its static type or its dynamic type?
Static.
It's static type. So when we're down here, how do we know which sort algorithm is going to be executed?
It's based off of which?
It's based not off of its static type, but off of its what? Dynamic type, which could have been any one of these.
Right.
Now, is everybody clear on this? This is going to happen over and over and over again. This is abstract versus concrete, and this is object-oriented programming, object-oriented design. All right? So now let's go ahead and run this and see what it does. So we'll do run. Now, and enter array capacity. We're going to do 50, and then file name, and we'll do this I050. And this program prints out the array, and notice that it got these from the file, and let's just do M for merge. And so you do merge, and boom, there it is. So now, with this particular project, I don't have a set of unit tests for you, all right? So the only way for you to test this is to do it with, I recommend you do it like with 50, or some big number like that, and just you can visually make sure that they're all sorted. And it's easy to kind of get it wrong. I've seen some programs that get handed in that it's okay except for the last one, and people just really quickly scan through and they thought it was correct. But make sure it's working correctly. You can just scan through there and see that they're all in order. All right? So that's the end of the demo. Okay, so that's the demo. Now, are there any questions now then about how to test your program and do it like this? Sorry, did you have a question?
Yeah, just kind of a general
Oh, that's a good question. In other words, why did we structure a sorter and sort int to be different projects? Very good question. Excellent question, as a matter of fact. Because we are also going to use a sorter with another project. In fact, the other project that we're going to use it for is going to be a project that uses these sorters to collect performance data on the different sort algorithms. And not only that, you are going to collect the data and write a little research paper using that data. And so the answer is that A sorter is going to be reused. Yeah. And so previews of coming attraction, that was a good one. That was a really good question, actually. Yeah. Okay, so that was good. Any more? Okay, so now, and in fact, the reason we're going through all these different sort algorithms is because you're going to use them to do this, to do some performance experiments. Now, so the quicksort algorithm I have actually written for you, so the only thing we need to do is understand it, but it's a little complex, and so that's what we're going to do now. So over here in this slide, I have a picture of that merit sort taxonomy for the quicksort algorithm. And remember, the way it works is we have 731628554, that's the original unsorted list L. And then when we do the split, all the small ones are on the left and all the large ones are on the right. And what we have shown here is that the ones on the left are 3124 and the ones on the right are 7685. Now, let's think about this for a minute. How are we going to segregate those elements so that the smallest ones are on the left and the largest ones are on the right? We obviously are going to have to do what with each value? We're going to have to compare it with a what?
Key.
With a key value. Do you see what we're saying? All right. So my question is, what is that key value that you should use for the split? You see, like we're going to have to go through, it's going to take a loop. We're going to have to go through in a loop, and every one, we're going to have to compare it with some key value. Well, because, I mean, how do you know? You might have a whole bunch of really big numbers. You might have a whole bunch of really small numbers. They might be spread out one way. They might be spread out. How are you going to know which key value? Because we're going to have to compare them. All these sorts are pairwise comparisons. So how are we going to know which one, what the key value to compare it with? How do you think we should, how could we do that? How could we figure out the key value?
You said average.
That's a good idea. One thing we do is we could just add them all up, divide by how many there are, and take the average. Now think about that. Think about this for a minute. What if you had a bunch of values like 3, 9, 17, 81, 2, 95, 1,786,000? What would happen? You would average them all up, add them all up, divide by how many there are, and you'd have one really big, humongous what? Key. Are you with me?
Yeah.
And then boom, it'd be way unevenly distributed. How could you do it? What would you, instead of doing it that way, what would be another way to?
The median?
The median. Yeah. So actually, the best in fact, that would be the best value. It would be the median, right? Because why? What is the median? It's the one that has what?
It's the middle.
As many. The median is as many what?
On one side.
Below it as it has above it. So actually, if you did the median, if you did use the median, then it would be split exactly in half each time. So let's do the median. Well, then how would you compute the median?
You need to sort the list.
Yeah, well, the problem is the way to find the median, you sort it, you take the middle one. But the problem is we're trying to do what? We're trying to sort the list. See? So, there are several common techniques for estimating the median. Now, check this out. Some quicksort algorithms just pick the one at the end. Pick A sub h and say, well, you know, one is just as good as another. Well, I'll just pick this element that's in the list. And I just pick the last one. All right? And you could do it that way. You could say the last one is always the key, because, you know, if they're in some kind of like random order, you know, the last one is just as good as any other one, right? Another technique is to take at random, use a random number generator to select one of the ones in between L and H, and say, okay, I'll just flip a coin and pick this one. This one is the key. But now, what we're going to do is try to be a little bit more sophisticated than that. Another way to do it is to take at random 3 elements between low and high, between A sub low and A sub high, and find the what? Because with just 3 of them, it's easy to just code up the what, find the what? The median of those 3, and then use that one as the key. Are you with me? Okay, so this is another common technique for estimating the median. Because an estimate of a sample of 3 from a larger sample, we should be closer to the median than otherwise. You see? So that's the idea here is that the closer you can get to the median for each one, the better the sort will be. The more evenly divided the partition will be when you do the split. Okay, so that's what we're going to do, and we'll show you the code on how we do that in a minute. But start here in figure 4.13 is going to be a sequence of snapshots that show the split operation of the quicksort, right? Because the join is trivial. The join, there's nothing to do in the join, right? So let's suppose that we have this, we're starting off with low being 0 and high being 9, and the elements are 90, 20, 80, 50, 40, 10, 95, 60, 30, 70. Now here's the thing about the quicksort algorithm. Because we are choosing elements at 3 elements at random between low and high, and the median of that to be the key, it's impossible to tell ahead of time just by looking at the code what the key is going to be. Do you see what I'm saying? And furthermore, if you run your program twice and you seed the random number generator with a different seed, and and different random numbers come up, you're going to get, it'll always sort, but the splits will be different each time. So it would be impossible to predict. Now, can you tell me in figure 4.13b, this is after we do split A, low, mid, high. Can you tell me what the value of mid is? Okay, first of all, wait, before I ask that. First of all, you see the numbers 20, 50, 40, 10, 30, 60? Those are all less than the numbers what? 95, 70, 80, 90. So what did split give to the value of mid in this particular one? 6 is correct.
6.
It set the value of mid to 6, and it guaranteed that all the what? The numbers less than, between 0 and 6 are 0 and 5, yeah, mid minus 1, are less than the numbers of what? Less than or equal to the numbers of what? Between 6 and 9. Okay? So we'll see how, and I had to do that in a loop, right? Okay, and then how does the sort work? So here's a split, then what do? We recursively do what? Sort which one? Now what does the sort algorithm do? It recursively sorts the what? The left side. So that gets 10, 20, 30, 40, 50, 60. And then it does what? And that's A between low and mid minus 1. Sorts. And then it sorts between what?
Mid and high.
Mid and high. And that gives us what? 70, 80, 90, 95. And now what does the join do? It just doesn't have to do anything. So the code for join is going to be brace, brace. Open brace, close brace. It gets called by the sort algorithm, but it doesn't have to do anything. Does everybody see how that works? Okay. So now, you guys, here comes the code for doing the split in the quick sorter. Now check this out. Let's suppose that the initial list is 90, 20, 80, 50, 40, 10, 95, 60, 30, 70. And now comes this random thing. All right, so in part B of the figure, what the algorithm does is it takes a random sample of 3 elements. And in this particular case, can you tell, it says take a random sample of 3 elements and then swap the median of these 3 elements with A sub high. And then it sets key to A sub high. Now, can you tell here which element in part A did it determine was an estimate of the median? It was the 60, right? And then what it did is, in going from part A to part B, it swapped this. It swapped the 60 with the element at A sub high. So do you see that the 70 and the 60 changed places there? Are you with me? And from now on, throughout the rest of the loop, the key is going to be 60. So key gets A sub 60. So we're always going to compare everything with the key. Are we good?
Just A high.
Which is A high, yeah. But there will be, instead of always going to A high, we'll have a local variable called key, and we'll say key gets A sub high, and then that'll be this. So it will be 60. Okay? Now, here's what we're going to do. We're going to have a control, here again, just like with merge sort, there's only one loop, and it's for j going from what to what? The control variable in this algorithm is j. So j is going to go from where to where? From low to high. Right? So one low to high. Yeah? And the first thing we do is we initialize mid to low. Now, because remember, what is the job of split? It's to set the value of what? And because mid is going to be called by what? Called by value or called by reference? It's going to be called by reference because it's going to change the value of mid for the sort program. Are you with me? So here what we're doing is we're setting mid to to low. So we do mid gets low, j gets low. Right? Now this first one is it's a little bit hard to see how this starts off at the beginning. But what we do now is, because in part C, because j is equal to low, we compare the 90 with the what?
60.
With the 60, because 60 is the key. Are you with me? Now, is 90 greater than 60, yes or no? It is. Therefore, we don't do anything to mid, we just increase j by 1 as it's going through the loop. Are you with me? We keep mid the way it is. Is everybody clear? Now what are we going to compare? We're going to compare the what with the what. And the next time through, we're going to compare the what? The 20 with the what?
60.
With the 60.
And then are you going to switch the value?
And now we're going to have to do a swap. Now watch what happens. We're going to compare the 20 with the 60. And what happens is, because 20 is less than or equal to 60, what we do is we swap the 20 and the 90. And then we increase mid as well as j. All right? Now at this point, in part E of the figure, now what we have is, what do we know? Now we have three regions, right? The first region has the 20 in it, the second region has the 90 in it. So now what's happening, you see, is the smaller ones are going to be in the region on the left, and the larger ones are going to be in the region on the right. So now, j is 80. So what do you suppose is going to happen now? 80, we compare 80 with 60, right?
Yeah.
And is 80, and what's the compare? What happens?
J increases.
J just increases. You see? And when j increases, that's fine. 80 is where it's supposed to be. It's in the right one. Are you with me? It's in the it's greater than 80. And now what will we compare? The 50 and the what?
60.
The 50 and the 60. Ah! But now if we only increase j, that would put 50 in the what? In the wrong compartment. So you swap the 50 and the 90 and j sub mid. And then, so if you swap the 50 with the 90 and increase mid as well as j, then the 50 goes where the 90 was. The 90 we know belongs in the right half, or in the right one. And then when j goes up, we also increase mid. So now 90 is in the right spot and 50 is in the right spot. Is that slick? That is. I tell you guys, for years and years, I used to use several different algorithms for the quicksort. And when I found that this one came along pretty late, this having just one loop, you know, there are many different complicated ways to do this. I actually even used a textbook once, where the author did not prove the correctness of it, and it was incorrect. And it was a published book. And you know, I had this student, he came to me, Professor Warford, this doesn't work. Well, but did you get it? Did you do it from the book? Yeah, I did it from the, and I looked at it, I thought, yeah, this is exactly the way the book says to do it. And I found a bug. I found a bug. So, and this algorithm with this one loop is the best one I've ever seen. It's very nice. It's because you know that the loop just goes once. It's just one loop. And there are versions with multiple loops and a little loop and a loop and then after you do this one, you got to do this one, and yeah. So now what's the comparison? 40 with what? 60, and then what happens?
It's going to switch 40 and 80.
Switch to 40 and 80 and increase what?
Mid-NJ.
Mid-NJ. Is that nice? I think that's just the cat's meow. So that's H, and then here, let's do, so now what's going to happen? This is H, so now 10 and 60, so what?
10 is less than 60, so swap 10 and 90.
Swap 10 and 90. So now 20, 50, 40, 10, and then 80, 90, 95, etc. And then this time 95 is bigger than 60, so we just increase J, and 95 is right where it needs to be. Is that nice? And then we do dot, 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 and now what happens is, in the end, oh, by the way, what's going to happen when J gets to high? Let's think about this for a minute. What happens when J gets to high? What will the algorithm do? It will compare the what? So what's going to happen when J gets to be, what happens when J gets high? It's going to compare what? 60 with it, with what? With itself. And is 60 less than or equal to 60? Yes. So what will happen on the last comparison? It will always do what? It will always swap. Are you with me? Are you with me on that? So when it finally gets to the end, it will swap 60 with mid, because 60 is less than or equal to 60. So that, and then it will increase, mid. Now, does everybody see that? And so in the end, we said, you know, the mid has been set, and all the ones that are less than or equal to are, all the ones on the left are less than or equal to all the ones on the right of mid. So now let's take a look at the code. So here we have, all we have to do is split and join, and there's the override stuff. And now we have two additional lines here that are private attributes of the quicksorter class. We have random device, RDEV, and we have default random engine, RDEV. Now, the details of this, of how to use this, are in the book. But let me just say that what I'm showing you here is how to use the new C++11 random number generators, which are really, really good. The C++11 finally has given us a good library of random number generators. And what it does, it's a little complex to use, but there are many, many libraries out there who have substandard random number generators. And so this shows you how to use this C++11 library for random number generators. Basically, that RDEV, the random device, that is the way you get the seed. And depending on your computer system, the seed could actually be, it could come from the clock, the system clock somehow. Or some systems could have like a random noise generator that actually pulls it out of a physical process, some data from a physical process to make it unpredictable. That's the seed. And then there is an engine. There's a seed, and then there's an engine, and then there's a distribution. And then the engine is seeded, that RDEV seeds the random number generator engine. Okay? And now here in figure 4.16 more, there is an additional postcondition for the split. Because when you do a split with the quicksorter, the split guarantees that A low dot dot mid minus 1 is less than or equal to A mid dot dot high. In other words, this means all the elements in A low dot dot mid minus 1 are less than or equal to all the elements in A mid dot dot high. Right? And take a look here. This part of the code is finding the estimate of the median. So here you see this. So here's another part of the C++ random number generator library. You see this uniform int distribution? What do you suppose that gives you? A uniform distribution of integers. between, we're giving it low and high. Okay, so you can have different distributions. You can have Gaussian distributions, Poisson, you can have different distributions. Okay, but we want a uniform distribution between low and high. Okay, and then we have one local variable called MDN, which is going to be our index of the estimate of the median value. And then we have these 3 other local variables, median 1, median 2, and median 3. And when we say int median 1 gets distribution engine, what does that do? That gives it a random integer between what? Low and high. So that's how we pick the random one. And then median 2 gives another one, median 3 is another one. And check that out, the if statement. If a sub median 2 is less than or equal to a sub median 1, and a sub median 1 is less than or equal to a sub median 3, then what does that mean? Median 1 is in the middle of those, right? Or a sub median 3 is less than or equal to a sub median 1, and a sub median 1 is less than or equal to a sub median 2. That means, again, median 1 is between what? Between those two. So then what happens? Median gets median 1. And then we check otherwise, if it gets median 2, otherwise it gets median 3. Yeah? Okay, so that's not too difficult to understand. The next 3 items swap the estimate of the median with a sub I. So temp gets a sub median gets a sub I gets temp. So does everybody see then that puts the key at the last? Are we good? And now look at this code. Is this code short and sweet? Look at this, look at this. T, now what is T?
It's abstract. I don't like
That everyone says T key gets a sub I. What is T?
the key.
It's it's the type from it's the parameter of the C++ template. So in this particular example, what is the value of T? Int. Are you with me? So it's this we're saying int key gets what? A sub high. So there's key is a sub high. And then we initialize what? Mid gets what? Low. So remember how mid gets low. And now look, for int j gets low, j less than or equal to high, j plus plus. One simple little loop. And what? If what? A sub j is what? Let's think of the key. Do what? Temp gets a sub mid gets a sub j gets temp. Swap and do what? Mid plus plus. Otherwise, j just goes up and it...
Oh, I see.
Now, is that neat? That when I first saw this code after years of using, more complicated stuff, I thought, whoa, this is way cool. Yeah. It's amazing how algorithms, we're going to learn we are going to learn a particular algorithm for red-black trees that is a huge improvement over much more complicated algorithms that were used to do the same thing. It's amazing that we still, in this day and age, in the last 5 or 10 years, that improvements are still being made, discoveries are still being made at how to simplify these basic algorithms. Yeah.
So does this increase the performance of the quicksort?
We are going to look at the performance. We are going to write the recurrence. And you're going to take data, and yeah. So that was a good question. But now there's one more little tiny thing here at the bottom. One last thing that we have to do is this. Let's go back to this part K or part J of this. Let's suppose in the unlikely event that our key was the maximum value. Because what did we say always happened at the end? The last value gets compared with its what? With itself, and then it gets swapped with what? Mid. So what would happen in the extremely unlikely, but Murphy's Law, if anything can go wrong, it will. What would happen in the extremely unlikely event that the last one was the largest value? It would be compared with itself. It would swap itself with mid, and then what would we do with mid? Increment mid plus plus. So mid would be what? In that unfortunate situation, mid would be what? past what? High. So if we look this very last line, now you guys know the trinary operator? The C++ trinary operator, the question mark colon? It's mid gets what? High less than mid question mark? So what does that mean? If high is less than mid, mid gets what?
High.
High.
Else it's mid.
Otherwise, mid gets what?
Itself.
Itself, and nothing changes. And why do we have to put that in here? Because if A sub high contains the maximum element, we will do mid plus plus, boom, and then mid will be greater than high, and it can't be greater than high. Here, I have a picture of this. Oh, and look, here's join. That's your assignment, right? Join. Well, it doesn't write. All right. So now, see, there are two post conditions. One is that a sub L dot dot m minus 1 is less than or equal to a sub m dot dot h. So that's from the split in the quick sorter. So this is saying what? All the ones on the left are less. This is are not sorted. Are less than each one of the ones on the right. Okay, so that's from the split in quick sorter. And then from the general split one, we had, remember we said L is less than M is less than or equal to H. What did we always say? Can mid ever equal low? And the answer is what? No. So L less than M less than or equal to H. So that's from the general split. So what happens is we can see what this code does. So here's the code for the, this is the code for the split of the quick sort. And this code, T key gets A sub high, mid gets low, and then the loop. That guarantees that A sub L dot dot M minus 1 is less than or equal to A sub M dot dot H. And this is the one that we need to guarantee that L is less than M is less than equal to H. In other words, M cannot be bigger than H. Do you see? And what we have here in figure 4.17 is a picture of the, in general, of the three regions during the execution of the loop. So do you see that? And guess what we're going to have to write down? The loop what? We're going to have to write down the what? The loop invariant. So here we are in the middle of our loop, and we have the region from low, between low and mid minus 1. Each one of those is less than or equal to key. Between mid and what? J minus 1, right? Less than J, right? Those are greater than key. And then the ones between J and high, that's we don't know what. Okay? So these are the three regions during the execution of the loop. What happens is as J goes up and up and up and up and up, what happens? That unrestricted one gets smaller and smaller and smaller and smaller till we get to the end, and then those are the two regions after normal termination of the loop. What can happen though is if A sub high contains the maximum element, mid is over here, so we got to do the adjustment to make it down here. See? Is everybody clear on that? And now you guys, tell me, here's the code, here is the picture. You know what the question is now? What is the loop invariant? Now don't everybody answer at once. How would you write, I'm asking how to write down the loop invariant.
Would it be for all, like,
For all, yes.
variables?
No, I think what has to happen is you have to make a statement about the one on the left, and you have to make a statement about the one on the right. And let's use L for low, H for high, J for J, M for mid, and K for key. For all I,
Where greater than low.
so low is what?
Less than.
L is what?
Less than.
L less than
High.
greater than, or like
L is less than I less than or equal to high.
No, not high. Mid.
Sorry.
Mid. What is true? A sub I.
A sub J.
A sub I. No, we said K for key. No. No, the key is not an index.
Oh.
K is not an index. K is the key.
Okay, so
A sub I is less than K.
Yes. Okay. And then
And
and conjunction.
It's great.
Well, let's use I again. No, we can't use J because J is our control one. Are you with me?
Like two.
Yeah, because but they both have to be true.
One,
So for all I what? Between what?
mid and J.
So how do you say that? Range what?
I is greater than mid.
Yeah, mid less than or equal to I.
Less than.
Less than.
Yeah, less than J. What has to be true for each one of those? A sub,
A sub I is less than or
No.
equals to greater key.
no, greater than,
Greater
A sub
than
key.
or
I is
equal
greater than.
greater than key. Here it is.
Oh,
For all I, so here, do the one on the left. For all I, L less than or equal to I, less than M, A sub I is greater than or equal to K, and for all I, M less than or equal to I, less than J, A sub I is greater than K. Are we good? We need to be able to write this down.
So
This is the loop invariant. This is what has to be true. The reason we split it in two is because two things have to be true.
Yeah.
You see what I'm saying? So it's a conjunction of these two quantified
and if
expressions.
there's just one.
Like all the variables.
No, because that's not what the loop is doing. Look, the loop is comparing it says if A sub j is less than or equal to key.
Okay.
So you see, that's what the loop is doing.
Okay.
That was a good question. See, the question was, but don't we have to worry about all these ones compared to each other? But that's not what the loop is doing. It's comparing it with k. It's saying if A sub j is less than or equal to key. Right? Okay, well, I was hoped to get through a little bit farther, but I think this was good. We'll continue with this Thursday.